So last class we had completed up to what is potential due to a system of charges. That means when you make a configuration, then we are in a position to calculate what is the electric potential due to a system of charges. And the procedure that we followed was, initially we used to bring one charge. The first charge is brought. When the first charge is brought, there is no potential, there is no any charge in that area, so the work done is zero. Then you bring the next charge, then you calculate what is the potential developed due to that charge at any point. Then you bring the third charge. So based on that, we'll first attempt one example which is there in our textbook, okay, and slowly step by step we will try to attempt that. So let's first see the configuration that we have for this type of question. So our configuration is somewhat like this. It's a square. Our configuration is a square, all right? And we have got charges. We have a charge here, we have a charge here, we have a charge here, and we have a charge here. These points are designated as A, B, C, D. A, B, C, D, right? And the charges that will come are a plus Q out here, a minus Q charge out here, again a plus Q charge here, and a minus Q charge here, right? So let us see what it says. And the side of the square, this is a square, so the side is D. So let's first write down what are given. 4 charges are arranged in the corner of a side of a square. Okay, so let's write our given data. The given data is 4 charges. 4 charges, namely Q, minus Q, again Q and minus Q, and they are arranged at ABCD of a square. Of a square of side D. The measurement of each side of the square is D. Okay, fine. The question has got 2 parts. The first is find the work done to put together this arrangement. The first part is find work done to put together this arrangement. How much of work we are doing to put together this arrangement, okay? So we'll start working that, and our concept is that this arrangement does not exist. You have to create this arrangement. That means you have to bring one by one charges and place them in such a manner that they form a square of side D. So we have to make this arrangement, right? Now they've asked us what is the work done. So the first guess would be that the potential is always given by work done over charge. So the work done will be Q times the potential, right? And we will calculate the work done in such a way that we will calculate the work done for every single charge, and add up all these works. Are we fine? Work done is always Q into potential. This is something that is there in our memory, okay? Work done is always Q times the potential at a work done in bringing a charge at a point is value of the charge multiplied by the potential experienced by the charge at that place, right? So let's begin our process. The first process is we are trying to bring plus Q is being brought to A. Plus Q is being brought to A, right? When plus Q is being brought to A, there is no potential which is there at A at all. This is the first charge which is being brought. Therefore, the work done which I will share as say W1 will be equal to 0. Is this clear? We had done this in the previous derivation also. Neha, are you online? Is it clear? Okay, fine. Right? Then number 2. Number 2 is we are trying to bring negative Q to the point B. We're trying to bring negative Q to the point B. Okay. When you're trying to bring negative, keep on writing also. So when you're bringing negative Q to the point B, then Q1 is, plus Q is already at A. plus Q is already at A, right? So this is very simple. We will go by our basic thing. What is the work done in bringing it? Q. Q means this Q multiplied by the potential experienced here due to this charge. So the potential experience due to this charge, we knew it. Q times the potential. So what is the potential due to this charge here? Forget Q. What is the potential here? Q divided by 4 pi epsilon 0 by the distance. How much is the distance? D is the distance. Yes. So here we will say that we will have a potential which is W2, and our W2 will be our potential, our charge Q multiplied by the potential at B due to plus Q multiplied by, you can write this, multiplied by the potential at B due to plus Q, multiplied by the potential at B due to plus Q. So this value will be equal to how much? Negative Q multiplied by Q by 4 pi epsilon naught D, which is equal to negative Q square by 4 pi epsilon 0 D. Is this much understood or not? Okay. Clear? Fine. So keep this marked, because finally we have to add up all these things. Okay. So our third charge. Third. In the third, what we are doing, we are bringing plus Q is being brought to C. Plus Q is being brought to C. And here we should remember that plus Q is at A and negative Q is at B already. With this consideration, you are trying to bring in. So here it will be the work done, that is W3, right? W1, W2, okay, W3. W3 will be plus Q times the potential at C due to A and B, due to plus Q and minus Q at A and C. So here we are going to use that same formula R12, R13 in that manner. Okay. So let's try to do it. Our charge is plus Q and I'm trying to find out the potential. Let's say, so let's find out first, try to find out what is the potential at C only due to A. Potential at C, all right children, we are trying to find out potential at C only due to A. So it's like this. This is your distance now. So if this is D, this is D. What is the distance of this? Try to calculate. This will be D square plus D square, which is equal to how much? 2D square. Root of 2D square. That means this distance will be D root 2. Is this clear? Okay. So you're trying to find out due to this. So here it will be the potential due to this. So this potential is how much? This potential is plus Q divided by 4 pi epsilon naught. And here we will have D root 2. And then the potential due to this. And this potential is negative Q divided by 4 pi epsilon naught. This will be only D. Right? Is this clear? This is my W3. So W3 can be further simplified. If I simplify W3 and I take Q common, let's take Q common and let's also pull out 4 pi epsilon naught. Okay, if we take Q common and q means q square, so we can take q square common, and if we pull this out, then yeah, then we are going to get, so what type of charge did you bring here? This is plus q plus q plus q plus q square minus q square, so this will become 1 by d root 2, and this is minus 1 by d, 1 by d root 2 minus 1 by d. Okay, further we can further simplify it. This becomes q square by 4 pi epsilon naught. Now d can also be pulled out. This is 1 upon root 2 minus 1 upon minus 1, just minus 1. Is this much understood? Right? Now we will bring our fourth charge. Okay? So let's bring our fourth charge. This is D. So we are now, this is our fourth scenario. And let us also keep this marked, which we had just calculated, this one. This will also be needed by us. Okay. And we're going to find out our fourth charge now. Chaliye, let's find out our fourth. Number 4. Number 4 is a negative q being brought to D with plus q at A, minus q at B, and again plus q at C. Right? So here the work done, W4 will be equal to the charge negative q multiplied by the potential, or we can write it as the potential at D due to ABC. Potential at D due to ABC. So let's calculate. So if you look for the potential for A, what will be the potential? Negative q will be multiplied by q by 4 pi epsilon naught D. Then the potential due to B, the potential due to B will be plus of minus q divided by 4 pi epsilon naught, and this will be 4 pi epsilon naught, and this will be d root 2. And then the potential due to C. So the potential due to C is a plus q divided by how much? 4 pi epsilon naught, and it will be due to D. Right? So all will be q square, q square, q square. So let's say we take q square out, and we also take 4 pi epsilon naught D out. Then what do we get? If you take q square out, then here it will be minus 1. All right? This is the plus q square. So here we will have 1 divided by root 2. All right? Here we will have plus q, so it will be a minus 1. Clear? Is there anything else? No. So the plus 1 and minus 1 will cancel each other. So W4 becomes equals to q square by 4 pi epsilon naught D. In the bracket it will be 1 by root 2. Oh, minus 1 doesn't cancel. Minus 2. Sorry, it will be minus 2 plus 1 by root 2. So this is our fourth. It's very simple. You just need to have the analogy correct. So now they've asked us what is the work done to arrive at this configuration. So the net work done, W net, will be equal to W1 plus W2 plus W3 plus W4, which means if we try to look at W1, W1's value is 0. So let's pull up W2. W2 is negative q square by 4 pi epsilon 0 d. Negative q square by 4 pi epsilon 0 d. Negative q square by 4 pi epsilon naught d. After that we have W3, which is how much? W3 is q square 4 pi epsilon 0 d 1 by root 2 minus 1. Q square 4 pi epsilon 0 d 1 by root 2 minus 1 plus the last one, that is q square by 4 pi epsilon 0 d. This is negative 2 plus 1 by root 2. So if we take, say, q square by 4 pi epsilon 0 d as common, then what do we get? We get a negative 1, okay, which will be added with 1 by root 2 negative 1, which will be added with negative 2 plus 1 by root 2. Okay? So finally the answer comes q square by 4 pi epsilon naught d. Negative 1 is negative 2. Negative 2 is negative 4. Negative 4, and this will become 2 by root 2 plus 2 by root 2. Negative 4 plus 2 by root 2, which finally it becomes q square by 4 pi epsilon naught, and root 2 into root 2 is root 2, so root 2 minus 4. So the answer, root 2 minus 4. Yeah. So book has shown as a negative q square outside. We have done only with q square. The answer is all same. This is the total energy required to make this configuration. Simple, just calculate the potential q times the potential at the point due to all charges. This concept is like superposition. Go on adding the potential due to each charge. This was a part of the problem. So we have a B part of the problem also. So let's see what is the B part of the problem. The B part of the problem is, now that you have made this arrangement, okay. So the B part says, a charge Q naught is brought to the center E of the square. So we have come to the center of the square, and the center is E, and you have brought a charge Q naught. So let's write the given data for part B. Given charge Q naught is brought to E, which is center of square. Center of square means, simple thing is, it is equidistant from all corners or vertices. This is equidistant from all corners or vertices. Okay. The charge is brought to the center. How much extra work is required for this? How much extra work is required? That is the question, right? So we approach it in the same way. The work done for bringing Q naught to the center E is equal to the charge Q naught multiplied by the V at E due to A, B, C, as well as D. ABCD means the charges at ABCD. Have you understood this? Due to plus Q at A, minus Q at B, plus Q at C, and minus Q at D. This is what is the potential. So this tricky question. So it becomes Q naught, right? Let us say this is equidistant now, right? This is equidistant. So we can straight away say that let us take this distance as some distance R. Let's say this is R. So all will be R. Yes or no? Right. So it becomes how much? It will be plus Q by 4 pi epsilon naught R, then plus minus Q by 4 pi epsilon naught R, plus again Q by 4 pi epsilon naught R, then minus plus minus Q by 4 pi epsilon naught R. So the final answer becomes 0. Clear? This will cancel this, this will cancel this. Imagine it's like pulling a guy with equal force on either side. So the net force is 0. Elaborate problem. Understood how to do such problems. Bring each charge individually, considering all the charges present in its vicinity. ठीक है, बना लीजिए. Right, our next topic. Potential energy in an external electric field. Right? So there's a difference. Now this is so far what you used to do. So far we used to do it like this. See, we used to have some charge, say a charge plus Q out here, and you used to bring another charge, say Q naught. You are either bringing it from infinity to some position, say let's say this point is infinity, this point is B. This is all we have seen. And there is an electric field which is actually generated by this charge, which is the source charge, or the charge which is present in that area where you are trying to do. Now we are trying to see a different thing, but there were no other electric fields present. Now this consideration is such that you are trying to calculate the potential energy when an external electric field is already there. Means there is, whether it may be a charge or whether it may be an electric field which is very strong, and you are trying to move a charge from infinity to a point, and in that point an electric field, there is an external electric field already present. This is the difference. Okay, so the book says the main difference is that we are now concerned with the potential energy of the charge in an external field. The external field is not produced by the given charge. Your given charge is not producing. And it's not necessary that you are bringing a test charge. You might bring any sort of a charge. And that electric field is not being considered. It's like you are entering into someone else's territory where an electric field already exists. Okay. Now, the external sources may be known, but often they are unknown and unspecified. What is specified is only the electric field. So we will have this is basically a charge movement in a zone with an external electric field present. And we will not be bothered about which charge is producing this field. The zone where I am moving my charge has this electric field already present. Okay. And the electrostatic potential V due to the external affairs. Now, since this is present, this will also give rise to an electric potential V, an electric potential V. Try to understand. We are moving a charge in a zone. We are moving charge in a zone where there is already an electric field, and we are not bothered about the charges. We know that there is an electric field present, and this particular electric field will also have a potential created at that place. Wherever I'm trying to move it, at that place I may experience a potential V. Have you understood? There is an electric field here, and a charge is coming and getting placed here. At this place, there is a potential due to this field. That potential is V. Okay? So it says V. Now we assume that the charge Q does not significantly affect the sources. This is true if Q is very small, means our charge is not going to affect any of the electric field, this external electric field. But for that, our charge should be very small, or the external sources must be held by some other forces. So if Q is finite, now these are the considerations. So let's say if Q is finite, finite means Q is not a test charge, it is a charge with a value. If Q is finite, its influence on the external sources may still be ignored in the situation when very strong sources far away at infinity produce a finite electric field E of interest. So what this tries to mean is that if Q is finite, then impact of E on Q, okay, the impact of Q may still be ignored. If Q is finite, the impact of E on Q may still be ignored, where very strong, so it may be ignored. And finally, our system can be considered to just E and Q. No other influence is there. E is coming from very far off place, and E's value is fixed, and you have a Q, and there is no intermixing between them. Now, if Q is brought to a point P, right, with this assumption, have you understood? Impact of E and Q may still be ignored, and finally system only has one electric field which is prevalent, and you are bringing Q to a point E. It's something like this. Let's say this is a zone. This is a zone. In this zone, I have an electric field E which is present, and you are bringing a charge to a particular point P. A Q0 charge is being brought to this particular point P. Now, work done in bringing Q to P is Q times the potential at P is given by Q times the potential at P. So the work done is written like this. See, Q into VR. Where VR is potential at P. And r is what? R is the position vector of this point. So if there was, if you want to make it more simple, then you can have a Cartesian coordinate system like this, all right? And you can join this, you can join this point, and your, this is r. R is the position vector. V at a point r, either you can say P or you can say V at a point r. R is position vector with respect to some origin, okay, where you want to bring it. So nothing new you have discussed, that even if an external electric field is present there, then the work done that you have to do is Q times V into R. Is this clear? So we generalize this to arrive at an interesting concept, and let's see what it is. Now, instead of moving a charge, this charge is now replaced with an electron. This is replaced with an electron, right? So if an electron, so now what is the value of Q equal to? The value of Q becomes equals to 1.6 into 10 to the power minus 19 coulomb, because the charge of an electron is this much. Now if an electron is moved across, okay, so you just wrote that the work done is equal to Q times the potential, Q times the potential at a region R. Now say if this potential is 1 volt, say if this potential is 1 volt, right, and you are moving an electron in presence try to understand, what are you studying? You are studying electric potential in an external field. So try to map the concept now. If you are studying electric potential due to an external field, then there has to be, electric potential due to an external field. There is an external field. The external field will also create a potential. See, ultimately it is like this. This is your space, right? There is an external electric field E here already present. What are you trying to move? I am trying to move an electron. Where are you trying to move it? Moving it to a point P, where an external electric field is present. This external electric field creates a voltage at P which is equal to 1 volt. You are trying to find out then what is the work done. Then the work done, so this is work done, W means this is work done in moving an electron, or this will be accelerated, actually accelerating an electron, work done in moving an electron, okay, to a point of potential equal to 1 volt is same as energy gained by the electron. Work done is energy gained by the electron, and this will be now given as Q, which is 1.6 into 10 to the power minus 19. This is coulombs multiplied by 1 volt, right? So this value is known as 1.6 into 10 to the power minus 19. So it becomes volts into coulomb. This is known as 1 volts into coulomb, and volts into coulomb is what, beta? Volts into coulomb is joules, okay? So this is joule, and this unit in atomic physics is known as 1 electron volt. So write down 1 electron volt. 1 electron volt is written as 1 eV, which is equal to 1.6 into 10 to the power minus 19 joules. So you can write the definition. 1 electron volt is the energy gained by an electron, in moving in a, gained by an electron when moved in an external electric field that creates a potential of 1 volt. One electron volt, right? So see once again, what is the analogy of this? You're trying to find potential energy in an external electric field. How is it different from what we studied so far? So far, whatever we studied, there was no external electric field. If there were some charges present there, the electric field was only due to those charges. Now, there is an external electric field. So who is creating that? None of our body. We know that that zone, like there can be a magnetic field, there is an electric field pre-present, and you are trying to move a charge. Now, if an electric field is pre-present, this electric field at any point will create a potential. We say the potential at this point is given by VR, where R is the distance of this point from some origin. And you are trying to move this charge from here to here. When you try to move this charge from here to here, the work done is given by the charge multiplied by the potential out here. So we say it is Q multiplied by V at R. Now, another thing happens is, sir, if Q is not Q naught, if it is some finite value, does it have some influence? Well, we consider that there is no influence of E on Q naught, no matter how big this is. Either this E is due to charges which are far off away, or at infinity there is a fixed value only. So our system finally comes down, just there is the E and a Q. Both do not interfere each other. And at that place, we say it is Q into VR. What is the significance of this? If you replace this charge and you try to now bring an electron at this position, so the electron is moving where, beta? The electron is moving in a scenario where there is an external electric field, and it will move to a point, right? It will move to a point. Remember, from where the electron is moving, there also this E is present. It is not that the electron is coming from somewhere else. So this E is present in the entire region where you are trying to move this electron. Though I have shown the boundary out here, our E is present in the entire region, and the electron is moving in this vicinity of in this presence E region, and it wants to move to a point P. What is the voltage at this point? Suppose it is 1 volt. How much is the electron's charge? 1.6 into 10 to the power minus 19. So there is some work done. That work done gets stored as energy with the electron, and the electron's energy is known as 1 electron volt. So 1 electron volt is the energy gained by an electron when it accelerates. Rather than move, we should use the word accelerates in an external electric field, causing a potential of 1 volt. So you can show the electron moving within the space only. When you are drawing your diagram, you can show the electron. Otherwise, it feels as if there is no E out here. E is omnipresent, the electron is moving to this place. So 1 electron volt is the energy gained by an electron in moving in an external electric field that has a potential of, and moving to a point where the potential due to an external electric field is 1 volt. So it's given as 1 EV, and it is used in atomic physics. So they can use the words like tera UV, mega UV, right? Kilo UV. So 1 EV, 10 to the power 3 EVs is kilo EV. Mega EV is 10 to the power 6 EV. Each EV is 1.6 into 10 to the power minus 19 joule. Now, values we can remember very easily. Come on, let's write them. What is so difficult? You should know 1 EV. See, I'll tell you how to understand this. Children, this is the standard unit of work or energy. But when you will do problems with atomic physics, they will give you the energy in the terms of EV. 1 EV, right? So similarly, if somebody says kilo EV, that means 10 to the power 3 EV. If somebody says mega EV, it is 10 to the power 6 EV. With each EV equal to how much? 1.6. So if you want to see this in terms of joules, it becomes 10 to the power 3 multiplied by 1.6 into 10 to the power minus 19 joules, effectively coming down to 1.6 into 10 to the power minus 16 joules. Did you understand? Right? Similarly, they can tell you giga EV. They may also tell you tera EV. And if they tell you peta EV, okay? So much clear? Okay. Now this was potential energy due to potential energy of a charge. Potential energy of a charge in an external electric field. So what did you study so far? You studied potential energy due to a charge. You studied potential energy due to a charge in an external electric field, right? So when you have an external electric field, then how did you do it? You did it simply by calculating the work done, which is equal to Q times the potential energy due to the external electric field at this point R. Q times the potential. This is what we have done so far. Okay? Now we take this further and we try to same story like previous. Potential energy due to a system of two charges in an external electric field. Okay, nothing difficult. What did you do in the previous one, sir? In the previous one I had only an external electric field where I tried to move only a single charge. I had an external electric field where I tried to move only a single charge. So what are you doing now? Now, sir, I am having a system of two charges in an external electric field. So what do you expect? Sir, I expect that there will be a new potential energy configuration which we are trying to find out, right? So same story. Our story will be something like this. Let's have a setup. Our setup is somewhat like this. For any arbitrary sum origin O, what are we having? We are having two charges, and the two charges are respectively at positions R1 and R2. Let this be position vector R1, let this be R2, and we have two charges here, right? This charge is Q1 and this charge is Q2. And there is an external electric field E, which is omnipresent here, which is the external field. You are trying to create this configuration and you want to find out what is the potential. So step is very easy. What are the steps? Steps. Number one, let this position be A and let this position be B. Steps. So the first step will be bring Q1. Where do you bring it from? Infinity to A. Infinity to A. And you find out what is the work W1 you are going to do. Definitely you will do Q1 multiplied by the potential at A. By the potential at A. What is the potential at A? The potential at A is due to the electric field which is already present out here. Right? So I can replace W1 and I can write it as Q1 multiplied by the potential at R1. Have you understood this? Once you have brought A already, now Q2 has a dilemma. Q2 is going to find the effect of both. One is the potential at B due to the external electric field, which is VR2, and also the potential due to A who has already come. So this one we will just see what is the potential due to A. And for that, we always definitely will need something which is the distance between A and B. Don't you agree? And this will be given by R12. So when you calculate the potential due to A, then we use R12 and the potential that is at B due to this charge which is already existing. And that is given by V of R. So I will say my second step will be now to move Q2 from infinity to B, right? And what is there? A is already present. Sorry, we will say Q1 is already present at A and E is the external electric field. You have to take care of both these two. So now we would say the work done, W2 should be equal to what? Q times the potential Q2 times the potential Q2 times the potential at R2. This is coming because of E plus the potential at B due to Q1. Is this clear or not? Right? So next, consider bringing Q2 to R2. In this step, work is done not only against external field but also due to Q1. So work done due to external field is given by VR2 and work done due to Q1. So can we now say our W2 will be equal to Q2 times V at R2 plus Q1 Q2 by 4 pi epsilon 0 R12 whole square, R12 just R12, not square. Sorry, multiplied by R12. Tell me, bacha, is this clear? So you actually created a two charge system where this was work 1 and this is work 2. Now if you want to find out what is the total energy, it will be W1 plus W2, no doubt. Okay. So PE of the system will be given by total work, which is W1 plus W2. So we find that it is equal to Q1 VR1 plus Q2 VR2 plus Q1 Q2 4 pi epsilon naught R12. Dekho to bacha, have you understood this? Yeah, write it down. Understand and write down, don't mug up. I mean, concept is very simple. When you bring the first charge, acha, what did we see the difference here from the previous ones? Previous ones, when you brought the first charge, work done was always 0 because there is no field. Now already there is a field present, which is already there. So the first child, it's like a game where children are trying to frighten their own friends. The first boy gets into the vacant house. He does not see any witch out there, so he's very comfortable. The second boy who comes here, now the second boy will see the first boy wearing the mask of a witch. But in the second scenario, what happened? A witch is already present. The first boy himself has got frightened. Now the second boy will come and see the witch impact plus the mask of the second boy, of the first boy who is already dressed like a witch. So he will have impact of 2. So write down those expressions. After that, we see what happens to a potential due to a dipole. Fine. So we have one more example to solve here. Let's take that. Maybe dipole will do in next class. Okay. So we have to find out electric potential energy of a system. Let's see what is the system all about. The system has got 2 charges. There is a Q1 charge and there is a Q2 charge. The Q1 charge is 7 microcoulomb. The Q2 charge is -2 microcoulomb. Okay. And with no external field, oh, your life is easy. E external is equal to 0. Means this is like the first scenario. Placed at 9. Okay, your position coordinates are, the position coordinate of this is 9, 0, 0. Okay, position coordinate is 900 cm, and the position coordinate of this is 900. Right? So children, let's try to visualize our system first. Then everything will become easy. Right? It's a 3D space. So we are not bothered about the z coordinate. So we have got 2 charges and our charges are like this. one is at plus 9x, one is at minus 9x. Clear, bacha? So our concept is, this is Q1, this is Q2. We're going to create this system, and this is negative 9, 0, 0. This is 9, 0, 0. There is E external is absolutely equal to 0. You have to create this system. So when you create this system, first what will you do? You will bring, so there is no witch now out here in this spooky house. There is no witch. So Q1 is the happy child who will come. So work done in moving Q1 is how much? 0, right? See, things are becoming so easy now. So we break up it into steps. Our first step is we will bring Q1 to the position. Let's say this position is A and this position is B. So we bring Q1 to A, right? When you are bringing Q1 to A, the work done is equal to 0. Clear? Fine. And the second job will be you're bringing Q2 to B. Q2 to B. When you bring Q2 to B, the work done W2 will be equal to Q2 multiplied by the potential at B due to Q1. Yes or no? Right. So can we now take up, right? So this is W2, and the network is equal to the EPE of the system, which should be equal to W1 plus W2. Okay, beta? So let's do our EPE. The EPE of the system, electric potential energy of the system, is finally basically equal to W2. So what is W2? Take the value of Q2. What is Q2? Negative 2 into 10 to the power minus 6, this much coulomb, okay, multiplied by the potential experienced here. What is the potential due to this charge? So the potential will be, potential due to this charge is 7 into 10 to the power minus 6 coulomb divided by 4 pi epsilon 0 into how much is the distance between the two? No, what is the distance?
2
Distance? How can distance be 2 here? Attention in here class. हमेशा खाते मत रहो ना यार, irritation होता है मुझे. That's a very unhygienic habit. Half you will be pricking your teeth, bringing out stuff. Then you will eat this. Then with that hand you hold that bottle. That's why I say you please get your own bottle. There's a hygiene issue. I'm not comfortable with that, Sarthak. You're a grown-up boy. You'll be 18 years old now, in a few years from now, a few days from now. You pull out stuff, you hold that. Is it hygienic? I'm not okay. Get a bottle from your home and drink it. I'm not okay. I'm saying that. Many children go and hold this bottle. छोटा-छोटा चीज है यार, ये सिखाना पड़ता है क्या? It is not 2q. The distance is how much? 9 on this side, 9 on this side. 18. But they are in centimeters. We will convert them back to meters. Okay. So how much will be it? 0.18. Okay. So can I not write it as 18 into 10 to the power 0. So it's 9 cm added with 9 cm, 18 cm. 18 into 10 to the power minus 2, right? So many, it will be meters. Okay? So you can calculate this. So many joules. Do you want me to calculate to make your life easy? So let's do negative 2 into 10 to the power minus 6 into 7 10 to the power minus 6 divided by, multiplied by 9 into 10 to the power 9, 18 into 10 to the power minus 2. So let's solve all 10 to the powers first. 10 to the power minus 7 and minus 6 makes it minus 13. Minus 13, and this minus 2 will go up and become plus 2. Minus 13 and plus 2, minus 11. Minus 11 and plus 9, it is ultimately minus 2. Right? So it's 2. 2 9s are 18. 18 and 18 cancels each out and gives you minus 1. Minus 1 into 7 is minus 7. Check beta. Negative 7 into 10 to the power, getting minus 2, they are getting negative 7, 7.0, they are getting only 7 or some calculation error. 7 plus 5 is 12. 7 plus 6 is 13. 13 and minus 2 goes up. 13 and minus 2 goes up, brings it how much? Minus 13 plus 2, minus 11. Minus 11 and 9 is minus 2. And 2 9s are 18. 18, 18 cancel. So you have 7. How did they get minus 0.7? How are they getting minus 0.7? What did we do wrong? Any data? Charge values or how much? Did I write the charges wrong? 7 and minus 2. 7 and minus 2. Oh, both are micro. There I have gone wrong. Both are micro. No, so this is minus 6. Yeah. Minus 6 makes it minus 12. Minus 12 and this 2 will make it minus 10. Minus 10 and 9, which makes it minus 1. Sorry, it's minus 1. This is minus 1, which is equal to minus 0.7 joule. Clear? This is the first part of the problem. Now, the second part. How much work is done required to separate the two charges infinitely away from each other? Now the two charges have to be separated infinitely away from each other, and how much is the work done? Okay. Now see, the second question is interesting. The second question says, how much is the work done in moving the two charges infinitely away from each other? We always know change in energy delta U is equal to UB minus UA. Okay, how to use this formula? How much work done? Now this is a configuration. Right? From this configuration, where are you trying to move it? You are trying to move it to infinity. So what is the work done? Whatever is the energy at this configuration. So we would say this configuration is created. Now the delta U is nothing but the work done. Work done is the change in energy of the system. This is U current minus U infinity. Do you agree or not? The same formula. We have already created a configuration, and the configuration has an energy. How much? Minus 0.7. That is U current. And you want to find out how much work will I do if I separate these two charges at infinity. You take this configuration to infinity from here. If you want to take these two charges to infinity, means this one also goes to infinity, that one also goes to infinity. That means you are doing an external work which is equal to the change in work or the change in energy, the current energy of the system. When you go to infinity, there will also be some energy. So minus that energy. But our physics says that it is U current. The infinity energy is always 0. Right? Therefore, the work done that you will do, is equal to alternately, you just think, how much is the energy of this configuration? Negative 0.7. If you would have brought something to here, how much work you did? Negative 0.7. So if you want to take them for there, negative 0.7.